trend I want to go over today is ionization energy. Now, this trend is very similar to one we've seen already. See if you can figure out what it would probably be similar to when I give you the definition of ionization energy. Okay? God bless you. Ionization energy is basically the energy it takes to make an ion, ionization energy, right? How do you make an ion? You remove an electron. So the ionization energy is the energy it takes to remove an electron. Simple enough. Now, again, just like I did with electronegativity, I'll bet you guys can figure out the answers to each of my things in my notes are going to come up here in the next, 10 minutes. And it won't be very difficult. You just have to apply the prior knowledge you have of atomic size, shielding effect, and octet rule to this case. Think about it. How much energy is it going to take to pick an electron out of an atom? As I go down, well, first of all, what's the next thing that's going to come up? Group. Okay, so as I go down a group, what are you going to expect? As you go down a group, is it going to get easier or harder to remove an electron as you go down a group?
Easier.
Everybody agrees it's going to get easier. So the amount of energy it's going to take is going to be what? Less. So what will the next statement say? It's going to say from top to bottom within a group, ionization energy does what? Decreases. Why? What are the two reasons?
Shielding.
Shielding effect is one. Now, by the way, do be careful. I think Bo said it last time. Trent said it this time. People will do this and not get full credit due to the atomic size. What should you say?
Increasing.
Due to the increasing atomic size, the fact that the electron's further away. Okay, so there it is. It decreases from top to bottom due to the increasing atomic size and the shielding effect. And if you haven't already defined shielding effect, you'll want to define what the shielding effect is as part of that answer if I ask you to. You can't just write shielding effect. Okay, you know what I want for short answer questions. I've been very specific. I've gone over 4 tests already. I've given you back labs and told you why you got points off on those. So you guys are, I'm not going to do it for the rest of the year. I don't think there's any more tests. Maybe one more test I'll actually give back and go over because there's a reason to. The vast majority from now on, you know how I grade. I want very specific answers. Okay, let's go on. Well, so the next word is going to pop up here.
Period.
Yep. There you go. Okay. And I'll bet you can predict that guy. All you got to do is look at what happens across the row to the size, and it will help you predict it. And will also, those other two things, or one of those other two things comes into play as well. As I go across the period from left to right, what's going to happen to the ionization energy? The amount of it, is it going to get easier? First, think of it this way. Is it going to get easier or harder to remove an electron? Harder. So it will take more or less energy? More. So it's going to, what? Increase. Okay? Due to? 2 reasons.
Decreasing atomic size and shielding.
I knew I'd get that. And it's a great bad answer. I'm glad Emily said that. It's a great bad answer. Because she said shielding effect. People want to put it down everywhere. Shielding effect has nothing to do with going across a period. When you go across a period, you are not adding energy levels. You're simply filling up the one you had. But what does come into play is the what? Octet rule. So decreasing atomic size and the fact that guys want to have an octet. They want to be like the group 8 elements, noble gases. Oh, that's nice. We're all done, right? I'm going to just close everything up now. Unfortunately, not. It would be nice. But ionization energy has some weird stuff going on. And this is going to help to illustrate why I had you guys graph the stuff in the first place, besides the fact. Hold on a second.
Anyone that sold donuts or Horizons,
just write that down with some exceptions.
Today in room 2. Again, anyone that sold Krispy Kreme or Horizons may pick them up today after school in room 2. Thank you.
Okay? There are some very unique and specific exceptions to this, however. Let me explain. And it also illustrates a point I was about trying to make before the announcement came on. I told you a little while ago, why am I showing you those graphs? I'm showing you those graphs and making you interpret them because you're really bad at it. All right? But you know what? If graphs were useless and you were never going to use them anyway, who cares? Well, they're not. See, a lot of times when you graph information, when you chart it, you see things pop out that you would have missed otherwise. Check this out. You've already seen me chart atomic size and electronegativity, and you saw what they look like and you were able to predict them. We just did them last period. Look at this chart. Something pops out at you that doesn't.
They're not even.
There's something weird going on here. Something weird going on at the same places across that period, right? You didn't see this last time. I mean, things didn't go up perfectly, but they didn't go up like this. You know, maybe one guy didn't go up as much or whatever. And if you look at the atomic sizes over here, you'll have some I told you that kind of like, oh, this guy went up, this guy went down. They're not perfect. But here, that's a pattern. There's something going on there. We got to talk about this. And where is it happening? Let's see. It's happening between elements 4 and 5, and again between 11 and 12. Let's see where that is. Look at the periodic table. 4 and 5. I'm sorry, I said 11 and 12. I meant 12 and 13. Oh, sorry. 12 and 13. Okay? Between 4 and 5, it goes down instead of up. And between 12 and 13, it goes down instead of up. Right? 4 and 5, 12 and 13. There's a clue, too. Happens between here and here. It also happens again between 7 and 8 and 15 and 16. That's between 7 and 8, 15 and 16. Notice again, between the same groups. Something's going on there. I'm going to try to explain it to you. All right? But I wouldn't have noticed it, maybe, if I hadn't seen that chart. That's why we graph things a lot of times, so things pop out at you. Secondly, let's explain it. What's going on between these guys? Let me do that with these. Let's explain these exceptions. The exceptions, as I just showed you, occurred between group 2 and group 3. Let's talk about those first. They're the easiest to explain. Okay? The exceptions occur between groups 2 and 3. Let's just take one of the guys. I'm just two of these guys, beryllium and boron. See there? That's where they are. Beryllium. See where I'm going to take beryllium and boron. And I'm going to investigate something about beryllium and boron's electrons. In order to do that, I have to use some knowledge I got last chapter. Orbital notations, the one I just gave you the test on, the one we just gave back to you a minute ago. If I draw out the orbital notations for each of these guys, it's going to help me out. But before I do, let me just say this. Beryllium and boron should not be harder to remove an electron from. But for all that is good and holy in this world, it shouldn't be harder to remove an electron from boron. Let me show you what. Beryllium has got an atomic radius of about 111. All right, so he looks about like this. Boron has an atomic radius of only 82, so he's smaller. According to that, don't draw these. According to that, okay, if I have my nucleus in there, this electron's closer to the nucleus. It should be harder to remove this electron. Here's another reason why. Beryllium and boron's closer to that group 8 element, right? This is group 8 right here. Wait, I always do that. I don't know why. Group 8. Everybody wants to be like these guys, right? Boron's closer. He's closer to an octet. He's a smaller atom by all that we know about the atoms. Everything we know about the periodic table, and everything we know about the octet rule and the size. It should be harder to remove that electron from boron, but it's not. It's actually easier. You saw it on the chart a minute ago. So I'm going to investigate by drawing. Watch what happens. The electron notation for each of these guys. You all agree it would look like this? I'm going to draw it out here. Okay, everybody agree it looks like that? Draw them out. Now, finally, maybe some of you can see what's going on here. Can anybody see why, even though this is a smaller atom, even though this guy's closer to an octet than this guy, it might be easier to remove this electron than this electron? What do you think?
Because nothing else in the group.
Yeah, this guy is all by himself in a sublevel, in the P sublevel. Nobody else around him. This guy's paired up, and he's filled up. Actually, that S shape is filled. We already know that filled things and paired things tend to be more stable. That's one good reason. Don't write it down. I'm going to put them both down here in a second. Can you see another reason? Why? Where is this guy coming from versus where this guy is coming from? They're both coming from the second energy level, but one guy is in a different what? Orbital shape. This P shape we know, the P shape is not as stable, not as happy as the S shape. So those are the two reasons. Even though this is a smaller atom than this guy, even though he's close to an octet, turns out he's actually easier to remove an electron from because he's coming out of a P shape and he's not paired up or filled up in any way, shape, or form. That's the reason. Those are the reasons why. Okay, so write these down for the explanation. Okay. Filled and half-filled sublevels, as I just said, have extra stability. This guy is nowhere near filled. He has one electron in the entire sublevel. He's not really stable at all. This guy is a filled a sublevel is just another fancy name for the shape, all the positions of that particular shape. The orbital. Okay, all of the positions combined. That's what a sublevel. The S sublevel, the P, the D sublevel. I've been using that term, but I don't know if I ever wrote it down anywhere. That's one reason. Filled and half-filled. Oh, by the way, the half-filled part, I'm going to talk about that in a little bit. Secondly, different orbital shapes have different stabilities. The S is more stable than the P. It's not surprising that it's easier to remove this P electron than it is to remove one from the S, because the S is happier. You'd be happier to be in an S than a P. Anyway. All right, now I'm going to make a distinction before I go on and do some other examples of this, but I want to say something. If I ask on the test, or on a worksheet you're going to get tomorrow, and I know I'm going to ask this multiple places, why is it easier to remove an electron from boron than it is from beryllium? Or by the way, why is it easier to remove an electron from magnesium than from beryllium? Well, take a look. There's boron and beryllium, right? If I were to have drawn magnesium, see the same thing's going to happen? Watch. Magnesium has 12 electrons. Don't draw this down. I'm just showing you. But the last thing in magnesium would be 3s2, right? What's the last thing I'm going to write for aluminum, which is on the other side of him? I mean, I'm going to write this whole same thing out, 3s2, right? And then what? 3p1. So that's the last thing you're writing for aluminum. That's the why it's the exact same logic, right? You're removing from aluminum. It's going to be easier to remove it, right? Because you're removing it from the P. But if I ask you the question, why is it easier to remove an electron from boron than from beryllium? Here's what people will write down, and they'll be shocked when they don't get full credit. Because filled or half-filled sublevels have extra stability, and different orbital shapes have different stabilities. Why would that be wrong? Why would that be wrong? I'm looking at you. Most of you guys are looking at me like, wait a minute. I thought he was going to say something stupid. Why, writing exactly what I wrote in the notes, would be wrong if I asked the question, why is it easier to remove this electron from boron than that electron from beryllium? Jared.
Because you're not applying it, you're just
memorizing it. You're just memorizing it, you're not applying it to the specific situation. For example, you can't say filled or half-filled sublevels have extra. What you have to say is, the P, this electron's coming out of the P shape, and it's not filled. So it'll be easier to remove it from that because the P shape is not as stable as the S shape, and the one from beryllium is also filled sublevel. Okay? That's a specific answer. P versus S, beryllium being filled, boron not. By the way, the other place this happens about the half-filled part, I should mention to you there. Look here. Here's nitrogen and oxygen. That's the other place it happens, if you remember, between 7 and 8 and 15 and 16. The reason that happens there, I'll just get you a clean board here and show you real quickly. For a guy like nitrogen and oxygen, nitrogen looks like this. Don't draw this. Remember they go in one at a time before they pair up? That's nitrogen. Here's oxygen. No one would have had trouble writing this. Okay, here's the reason why in this case. In this case, if I were to ask you this one, whoops. Maybe. If I were to ask you this one, and that's oxygen right here, why is it easier to remove this electron than this one? Okay, well the reason is this. Has nothing to do with the shapes because they're both coming out of a P shape. It has everything to do with the fact that this half-filled sublevel is more stable than this guy. And this guy, by removing him, drops him down to being half-filled. Hund's rule said they go in that way for a reason. They want to they're more stable when they're filled or half-filled. Same thing would happen with the D as well when you have 5. And that's why I told you there were exceptions, like with chromium and silver, where guys really want to be half-filled. They'll actually take an electron from the S and bring them down here in chromium's case and in silver's case to get you guys to be half-filled or filled for the D. Okay?
So they either want to be completely filled or half filled.
Right, right. And so that would not, you could not use the fact that there are different shapes in this one because they're not different shapes for nitrogen and oxygen. All right. Now, good enough. Now last thing I want to do is summarize everything for you here because this is what you're going to have to do on the tests and on the worksheets and homework tonight. I will give you quite often multiple guys. I'll say this element. It's amazing. It's impossible, but it's amazing. I might pick that element out, whoever he is, a guy here and a guy here. Now, on the homework tonight, I'll do that, and in my worksheets, it's going to do it all the time. I'll say, here's sodium, here's oxygen, here's whatever. Of these 3 guys, who would be the best at this? Who would be the largest? Who would be the smallest? Who would be the strongest? Who would be the best metal? Who would be the worst metal? Who would have the highest ionization energy? Who would have the lowest electronegativity? You know where you're always going to be able to do if I ask a question like that? Who are you going to ignore if I ask that question? A, B, or C? B. Because every trend in the periodic table changes from down here to up here. The extremes are down here or up here. Now, I said the extremes are down here or up there. I did not say, like some people heard, the largest are always down here and the smallest are always up there. If I'm talking about atomic size, where is the largest atomic size? Down here. This is the highest atomic size, atomic radius. But if I'm talking about ionization energy, what is this down here for ionization energy? It's the lowest possible ionization energy, right? What if I'm talking about electronegativity, highest or lowest down here at the bottom? Electronegativity is the attraction for electrons, right? So it would be the what? Lowest electronegativity. How about if I talk about the best or the worst metals? Where are the best metals? What do metals want to do? They want to lose. Where are the best metals going to be? Down here. So notice, sometimes it's the biggest or best down here. Sometimes it's the worst down here. It depends on what you're talking about. But the extremes are always going to be up here or down there. You can kind of ignore the elements that I choose in the middle of the 3 I give you, right? That's just a little hint that you can use, I hope, throughout. And I will ask those kind of things from you. Let me ask you again in terms of these charts. Okay, look at this chart here. If I pointed at this guy right here, oh, sorry. Say I pointed at this guy right here. It's amazing. I mean, I hit the button. You got to be kidding me. Who is that? Well, I gotta choose an easier one to say. This guy right here. What do you think he is? Lithium, because here's 2, that's 1 over, it's lithium. And this guy over here would probably be what? 18. 18 is argon. Okay. Which trend is this? We have 4 possibilities now. What trend do you think this is? Well, what's it doing across the period? Increase. Does atomic size increase across the period? So we know it's not atomic size. Do you get better metals across the period? So we know it's not a metal. What about electronegativity and ionization energy? They both increase across the period, and they both decrease down a group. So I've narrowed it down to electronegativity or ionization energy. Which is it? Why? How do you know it's electronegativity and not ionization energy?
Because
there's no exceptions, right? Where it goes down and down, and it doesn't do this. Remember? Okay? Emily is on her game. If it were electronegativity, it would look like that. I'm sorry, if it were ionization energy, it would look like that, right? Now, by the way, I've been showing you the same basic charts just to get used to it. But as you just seen, as I flip through these, and I'll do this tomorrow too, I can show the charts in a lot of different ways. You're going to have to get used to seeing it without just the same. Because honest to God, I've actually had people do this. Well, I knew it was electronegativity because it's green, and the ionization energy is yellow. I swear to God, that happens. That one's green, and the ionization energy is, actually, that one's not yellow, but the other one was yellow. Atomic size, I think, was yellow. All right, well, we're not going to get that now. All right, good enough. Let me get you